Welcome to 11.5. Now this video is going to be I'm going to talk rather fast because there's only 6 slides. I'm going to try to keep this under 15 minutes. So all the series that we looked at so far had positive terms. So in this section, we're going to have alternating terms. So hence the name alternating series. But as long as your series decreases towards 0 in absolute values, that means if it didn't have the signs on it, then the series converges. So you're going to see a -1 raised to some power being multiplied to some sequence function, hence the pluses and minuses. But your original sequence function b sub n is greater than 0, which means it always generates positive terms. So if we can satisfy one, that the limit as n goes to infinity of the original sequence function without the -1 attached equals 0, and it's decreasing, that's what this notation means, that the very next term has to be less than or equal to b sub n for all your n, then the series is convergent. So what's happening here is if you look at a picture of what's going on, if we start at 0, you add b sub 1, then you subtract b sub 2, and you add b sub 3, subtract, add, subtract. Well, your partial sums go s sub 1 is big, but then s sub 2 is small. That's the second partial sum. Then the third partial sum is bigger, then the fourth is smaller, then the fifth is bigger, sixth is smaller, and it keeps alternating back and forth to where your sum is going to converge somewhere here in the middle. So let's look at some tests. So we're going to abbreviate this as AST in our justifications. So we saw in the past that the harmonic series diverges. Well, now that it's alternating, let's see if it's going to converge. So 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, so on and so on and so on and so forth. Take the 1 over n, that's your b sub n, take its limit. Well, we can clearly see that it's going to 0 because the top stays the same while the bottom gets bigger. And now we have to see if it's decreasing. So if it's a nice polynomial function here, what we can do, polynomial on the top and on the bottom, you just substitute n plus 1, that notation in for n, to create your new sequence function. And now that it's a technically proportion, take this n, multiply it to the upper left-hand corner, take this denominator, multiply it over here, you get n is less than or equal to n plus 1. Subtract over the n, you have a numerical statement that is true. So both 1 and 2 are true, and therefore on the test you would write the series converges by the AST, and you give me the series. Just rewrite the question in your answer. Okay, example number 2. Here's my -1 to the n minus 1 power. Here's my b sub n. Let's take its limit and see where we're going. So as infinity goes in for n, wait a minute, the top stays the same, the bottom's getting bigger, which means the fractional power is approaching 0. So this is e to the 0, which is equal to 1. Step 1 is not satisfied. It's not equal to 0. There's no need to do number 2. And if you remember from the past, this is our divergence test. If you take the limit of the function and you get anything and everything except a 0, then this diverges. So if this b sub n is going to diverge, then a -1 to the n minus 1 power multiplied to a diverging sequence is still going to diverge. Okay, example 3. Oh, here's my -1. Now it's raised to the n power. Doesn't matter. It's still alternating. Here's your b sub n. Let's take its limit. 2 approaches to this. Some instructors have told you that when you deal with square roots, go to the denominator, find the n term to the biggest power, and you divide all your terms by that power. That's what the red n is for. And then you simplify all your fractions. Well, technically, this is going to be 1 over the square root of n, and that approaches 0. N's cancel, that's 2. This approaches 0. Same situation as on the top. So you have 0 over 2, that's equal to 0. Or another approach that you could look at is change the square root of n to the 1/2 and use the principles of your horizontal asymptote rules. It said as long as the top power on the leading term is less than the power on the bottom leading term, then your horizontal asymptote is y equals 0, and therefore that's your limit. Okay, decreasing. This is going to be difficult to plug n plus 1 into that n right there because you are going to not have like radicals when you try to solve this. You won't be able to get things to cancel. So here what we might want to consider doing is changing it to a function f of x and taking the first derivative and use the first derivative test. So the 2x plus 3 is squared on the bottom. I know this is here. I'll explain it. Give me a sec. Then you take 2x plus 3 in the top and you multiply it by the derivative of the top. So the derivative of the square root of x is 1 over 2 times the square root of x minus then the square root of x times the derivative of the bottom, which is 2. So we have minus 2 times the square root of x. Well, to get rid of that 1 over 2 times the square root of x in the denominator, you multiply top and bottom by 2 times the square root of x. When you multiply that to everything on the top, it simplifies to 2x minus 3, or negative 3 plus 2x. And to make this less than 0, this is the only place to show negatives, so set that top equal to 0. And we get x is greater than 3 halves. So therefore, b sub n is decreasing for n is greater than or equal to 2. And what's interesting here about this is that as long as it's going to be decreasing, it doesn't matter at what n it occurs at, because we're going out to infinity. As long as we can get that thing to start decreasing, then it's going to be decreasing, if you will, for the whole thing. So therefore, both statements are true, and therefore our original series is going to converge by the alternating series test. Example 4. Here's a case where now we don't have a negative 1 to raise to a power. It's in our base already. So what we have to do is factor the negative 1 out to the n power. And that 3 to the n now becomes my b sub n. So let's take its limit. And I just realized that will be infinity over infinity. That's a indeterminate format. So we're going to have to do L'Hopital's rule. So I like to do L'Hopital's rule as true functions. So that gives me the derivative of 3 to the x is 3 to the x, but then times the natural log of the base that you're using. The derivative of x is 1, and as you can clearly see, this is going to infinity, which does not equal 0. It doesn't exist. So no need to do step 2, and as we saw earlier, this is going to diverge because of the divergence test. All right. Okay, example 5. Wait a minute, where's my negative 1 raised to a power? Wait a minute, I think it's going to happen with cosine, because we know cosine starts at 1 and goes down to negative 1. So let's look at cosine of n pi, and let's make a little chart here. N is going to be a 1, so 1 pi on the inside of the cosine function. Cosine of pi is negative 1. Put the 2 in for n. Now cosine of 2 pi is 1. Put in the 3. Cosine of 3 pi is like going back to negative 1. Cosine of 4 pi, that's 2 revolutions around, back to 1. Well, this is going to continue on forever. So the cosine of n pi is technically your negative 1 to the n power. So n over 2 to the n, that's your b sub n. Let's take its limit. And again, just like up here, we see that it's going to be infinity over infinity, so we're going to want to do L'Hopital's rule. And we get 1 on the top. We get 2 to the x times the natural log of 2. Again, we can see that the bottom is going to be getting bigger than the top, and therefore this approaches 0. So now it's off to do step 2. We want to show that n plus 1, remember we got to take n plus 1, put it in for both n's, is less than or equal to the original b sub n. Here, we can manipulate this denominator on the right to be the same as on the left, as all we have to do is multiply top and bottom by a 2. Because when you multiply like bases, you add exponents, and that's going to give me n plus 1 as a power on that 2 in the denominator. So therefore, I now have n plus 1 is less than or equal to 2n. Well, if I subtract over the n, that's 1 is less than or equal to 1n, and that's going to be true for all my n. So both statements are true. Therefore, our original series will converge by the alternating series test. And again, yes, you write this all down on the test. Example 6. All right, there's my negative 1. Let's get that out of there. Here's my b sub n. Well, I can see this right away. Top power smaller than bottom power. Let's take its limit. It's 0. That's your horizontal asymptote rule, as we talked about earlier. Now, let's show that it's decreasing. And I'm going to hold off here a little bit. I don't think I want to put this n plus 1 in for that n, because that's going to be a binomial squared. N plus 1, all that cubed. I really have no desire to multiply out 3 binomials and 2 binomials and combine like terms. And not happening. You could. Way too much work. So again, consider it as a function, and let's take the first derivative by the quotient rule. You'll get x cubed plus 4 squared on the top. We'll have bottom x cubed plus 4 times the derivative of the top, 2x, minus x squared times derivative of the bottom. Multiply that in. Now that's easier multiplication, folks. So 2x times x cubed is 2x to the 4th. 2x times 4 is going to be 8x. Negative x squared times 3x squared is minus 3x to the 4th. Combine that together, we're going to get 8x minus x to the 4th, and we can factor out an x, and we have 8 minus x to the 3rd. And if we want this to be less than 0, this is the only place we can create negatives, since we're starting with n equals 1. So we'll set 8 minus x to the 3rd less than 0. Okay, solve it. Take the cube root of 8. It's 2. However you want to move that over, just remember when you divide by the negative, that's what you're doing. You got to flip that inequality symbol. So like we saw earlier, it doesn't matter when it happens as long as it's going to happen. So therefore, n has to be greater than 2 to get this to be decreasing. It's going to happen. So our series is going to converge by the alternating series test. All right, now in my last example here, now we have an alternating series estimation theorem. Remember I was talking before that this S is eventually going to converge somewhere? Well, we don't actually know what that S is, but we do know the following. That it's going to be really, really, really close to this situation right here. R sub n. All right, that's going to be the remainder of the difference between the S minus S sub n. That's this S minus one of these two S's, whether on the left or the right. And that's going to be less than the last B that we look at. So notice that B sub n plus 1 is not part of the partial sum of S sub n. All right, so that's the sum of my series. This is going to be the absolute value of the first neglected term. Okay, so how that works is as follows. Let's say n is 5. So here's S sub 5. S minus S sub 5, that distance is definitely smaller than the distance of B sub 6. Everybody agree with that? That's what we're measuring. And if we did S sub 6, then B sub 7 would be to here. And that distance is shorter than this distance. All right, so the partial sum S sub n can be a useful approximation for the sum of the series. The error involved is your R sub n absolute value equals S minus S sub n less than or equal to that next term that we're neglecting to look at, the B sub n plus 1. Well, when we have absolute values, you got to have a positive case and a negative case. So what we're going to do is we're going to write this as negative B sub n plus 1 less than or equal to S minus S sub n, the partial sum of n terms, less than or equal to B sub n plus 1. And this will find us really close to what our sum is going to be within a given error range. All right, so to solve for S, we add the S sub n to both sides, and this will give us a good idea of where our sum is going to be at. All right, so here's an example. How many terms of the series do we need to add in order to find the sum of the sum to the given accuracy? So here's my error, 0.0001. So I want my error to have 4 zeros in it. Okay, so we're going to take our series here, and we're going to start finding terms. So b sub n is 1 over n times 5 to the n power. So let's find b sub 1. 1 over 1 times 5 to the first. Notice I'm leaving off the negative. I don't need that right now. b sub 2, 1 over 2 times 5 squared, 0.02. And you can leave these as fractions too, but we really want these to be decimals in here because we're looking for when do I get 4 zeros to the right of the decimal point. b sub 3, 1 over 3 times 5 to the third, 0.0026, repeating, getting closer. b sub 4, 1 over 4 times 5 to the fourth, 0.000. I think we need to go b to the fifth, ding, 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 ding. 1, 2, 3, 4 zeros. All right, that's going to be less than 0.0001. All right, so this is going to be my left out term. So we're going to go to 4 terms. That's what we have to add up together. Thus, the error message is less than b sub 5. That's what we're looking for. So we need to add 4 terms. So the fourth partial sum, now we bring our negatives back. When n is 1, we have a negative 1, so that's negative 1/5, plus 1 over 50, minus 1 over 375, plus 1 over 250. My calculator told me a negative 1,367 over 7,500. All right, which is approximately this decimal. So we bring in our compound inequality to find s. We know our s sub n. It's this fraction. We know what our b sub n plus 1 is. Right there, 0.000064. So those are our terms. S sub 4 here minus b sub 5 here. Okay, so there's the decimals, and where I got the decimals is I simply went to my calculator, typed in that s sub 4 minus 1 over 5 to the 6th power, because 5 times 5 to the 5th is 5 to the 6th. So negative 0.18233066667 will be this term, and negative 0.182202667 is going to be this term over here. So since we're looking at 4 decimal places, 1, 2, 3, 4, 1, 2, 3, 4, my sum of this series is somewhere between these 2 decimal values. So that gives us a really close example where things are at. Okay, again, it should be noted that the rule that the error in using s sub n is an approximate s. All right, it is smaller than the first neglected term in general, valid for alternating series only. Okay, this rule does not apply to any other type of series. Okay, all right, thank you, and I'll see you in the next section.